Good morning, everyone. I think this streaming is going to start at 10 o'clock right now, so we might as well synchronize to that. Good morning, everyone. Welcome to the Max W. Brown atrium of the MSWE building here on Purdue campus. And if you are online, welcome as well. We have a lot of caffeine drinkers in the back next to the Starbucks. Where's the line? Usually the line goes all the way out to Hufty. Well, this morning, we don't need caffeine to wake up to such an important, exciting celebration. Somewhat belatedly, perhaps. It happened actually a year ago on both successes we're celebrating, recognizing this morning. But now with COVID under control, we hope to be able to do all of those celebrations. So we started doing this with the 2017 fall win of the National Science Foundation Engineering Research Center, ERC, led by Fabio Roberto in chemical engineering. And ever since then, we've been doing this with a somewhat arbitrary definition to say that if this is a nationally competitive center by federal or private sector with $10 million or more in total, led by Purdue faculty members, then we will throw a party. This is not to say that if yours is $9.8 million national center, we don't recognize it. We absolutely appreciate research excellence and the pinnacle of excellence at scale in all forms and shapes, including theoretical research that is not reflected in the funding amount. But having said that, we do also recognize these very competitive successes. So, Executive Vice President for Research and Partnership, Dr. Teresa Mayer, and I have been working together, and we reviewed the major wins of that type in the past year or two. And within engineering college, we have 7 or 8. So we thought that to cut cost on water and coffee, we're going to bundle some of them into 4 celebrations. And this is the third, this AY, out of those 4, and the theme is semiconductors. There are the actual experts, such as Mark Lundstrom and Teresa, who can say a lot more about that. Let me just highlight my understanding as a layperson that this is so important that it is essentially the foundation of all the digital economy for this country and for the free world. And Purdue is proud to have arguably one of the highest concentration of faculty, staff, and student talents. Still, it takes a lot of whole village effort to win any of these centers. The 2 we're celebrating today, one is SCALE, one is the Center for Secure Microelectronics Ecosystems, ties into the Department of Defense, ties into private sectors such as TSMC, the world's leading semiconductor manufacturer. And when we celebrate these hard work and their results and impact to society by our colleagues, we also recognize that there are multiple tracks to what Purdue and Purdue Engineering College are embarking on in semiconductors. One track is workforce and education, including SCALE, and I think of all the existing and ongoing discussion of workforce for semiconductors in this country, Purdue is the only institution participating and leading in all of the conversations. And it is a reflection of our tradition in excellence, such as NanoHub, online learning, residential learning, including the latest dedicated degrees to semiconductors, the first of its kind in the country, across multiple schools and disciplines, launching right now. And Dimitri can tell you all about that a bit later. Now, there is a second track, of course, of research. And if the CHIPS appropriation can ever happen, and I do think it will happen this year sometime, perhaps in summer, it will then spark even more resource dedication from the federal government. And then we have a very supportive state of Indiana government, IEDC, along with many private sector partners, such as those in SRC. So clearly, we're going to win a lot in the coming months and years in semiconductors across multiple dimensions, from neuromorphic computing applications to a back end of line, to development, to packaging, and many more. And third is the industry engagement. We want them to come here to work with us. We want them to come here and create jobs and knowledge together, to retain the talents that we're going to train in residence and online. And we're in conversation, along with Teresa, in many stages of discussion with multiple such leading companies around the world. So it's truly an exciting and critical time for chips in America, and Purdue, again, is shouldering an extremely important, unique responsibility. So the two celebration today touches two important tips of an ever-growing iceberg that is going to be changing how this country and the world will be embarking on the next journey of digital economy here. So I'm going to now turn the table first to Mark, and then have Teresa wrap up this morning's hour-long session. Now, Mark, I have to say this every time. Sorry, Mark, I know you don't like it, but not only Mark was the acting dean for this great college, and during my year in DC, he also has kindly agreed to take on this responsibility to help coordinate across many different schools in college, and more than 30 different faculty members. As you know, more than 30 faculty members, that's as complicated as the United Nations diplomacy. Mark actually started sabbatical very happily for about 6 days until he received a phone call from me to say, well, Mark, I know you're on sabbatical, a well-earned one, especially after the acting deanship in 2020. But would you mind to help out in this additional way? And Mark kindly agreed, and ever since he's been only working 24/7 every week. Thank you so much, Mark. And Mark will also introduce 4 outstanding panelists, and I think that's Peter and Carrie for Scale, and Jorg and Anand for the CSME. These two particular celebrations we recognize today. Again, we thank all of the faculty, students, and staff and partners when it comes to the resurgence of semiconductor excellence in the country and the singular pinnacle opportunity for Purdue. Thank you, Mark.
All right. Thank you, Mung. You really don't need to do that. Good morning, everyone. So it's a pleasure to be here. What we'd like to do now is to have a discussion on the future of microelectronics with 4 leaders of these 2 initiatives. Let me first of all begin by bringing the panel up to the stage. I'll introduce the panelists. First of all, Jorg Appenzeller. Jorg is the Barry M. and Patricia L. Epstein Professor of Electrical and Computer Engineering and co-director of CSME. Jorg? Second, Anand Raghunathan. Anand is the Silicon Valley Professor of Electrical and Computer Engineering. He's also co-director of CSME and also is the Associate Director of CBREC, another one of our microelectronic centers. Peter Bermel. Peter? Peter is the Elmore Associate Professor of Electrical and Computer Engineering and Director of Scale. And Carrie Douglas. Carrie is Assistant Professor of Engineering Education and Director of Internal Assessment for Scale. So we're looking forward to an interesting discussion. We're at a very interesting and important time in microelectronics. We're really at an inflection point for 2 different reasons. First of all, after 50 years or so, in which the driving force for progress in microelectronics has been making transistors smaller and smaller and putting more and more of them on a chip. That work has created the sophisticated electronics that we see all around us, the underpinnings of our modern digital economy. But it's also created an enormous appetite for more and more computing power, more and more data storage. But we're entering a new era in which it's getting very difficult to make transistors smaller. It will be only one of the several ways in which progress continues. New ways to advance electronics must be found. The second reason that we're at an inflection point is that as a nation, we've learned how dangerous it is to be critically dependent on a critical technology with overseas suppliers. Congress is preparing, and we hope it will happen very soon, to make a national commitment to bringing microelectronics manufacturing back to the U.S. Doing this will require a highly talented and substantially larger workforce. The estimates that I hear is that we will need 50,000 new semiconductor engineers over the next 5 years to ramp this up. That's an incredible challenge. And Purdue has made a commitment to play a major role in addressing that challenge. So there are two broad questions for our panels. How will microelectronics advance when making transistors smaller and smaller is no longer the main driving force? And how can we rather quickly develop a substantially larger workforce? And how do we prepare them to advance electronics in new ways? So I'll begin. And let me begin with Jorg and Anand, and then ask others to comment if you'd like to. I know that in your research, you're exploring several different ways to advance the performance of electronic systems. So my question for you is that when you look back in 10 years, in 2032, when the power of electronic systems has progressed enormously and dramatically from where we are today, what are the one or two ways that you think this progress will have occurred? So let's begin with Jorg.
Thank you very much, Mark, for the question. It's a great pleasure to be here. So it's a difficult question, of course, to ask, and I've been long enough around to have seen that there is a certain stubbornness in the industry when it comes to introduction of anything that is truly novel and innovative. But I think the semiconductor industry has realized that we are now really at this inflection point, as you called it, where novel types of materials, emerging technologies that have been deemed in the past to be too difficult or maybe too expensive to implement will become part of the real heterogeneous but monolithic integration of future chip designs. I'm saying that having worked, for example, for a long time on carbon nanotubes, and now I'm seeing companies that are using carbon nanotubes for memory applications, and they're getting closer and closer to the real application space. Magnetic tunnel junctions also have evolved to the point that we are now talking about MRAM. These are all novel types of concepts that could only be introduced because of the fact that we are now at that stage where the industry is hungry to look for alternative solutions. Thank you.
Okay, thank you, Jorg. So I'll just point out, Jorg works on the physical side of microelectronics. Anand works on the design and system side. So we'll ask Anand for his perspective.
Thanks, Mark. So yeah, naturally my perspective is going to be shaped by where I come from. But I think looking back 10 years from now, I think the progress in this coming decade will largely have come from co-design. And what I mean by that is really optimizing microelectronic systems at different layers of abstraction across technology and design. We're already seeing examples of that. The tremendous progress in artificial intelligence and machine learning is powered by improvements in compute. And most of those improvements are not just from the raw transistor performance improvements, but really from matching the hardware, the architectures, to the algorithms. Okay? That's just one example. And when you go from algorithms to architectures to circuits and then the devices, there's plenty of opportunities for co-design across the stack. So I think that is going to be one major source of improvement. I think the other is, although individual transistors may not be getting smaller, I do think we will be integrating systems at larger scales. And I think packaging and heterogeneous integration is going to be increasingly important and enable some of those advances as well.
All right, thank you. All right. Okay, let me ask another question. And this one, let's begin with Carrie and Peter. Over the last 30 years, microelectronics manufacturing has been outsourced, and as that has happened, student interest in pursuing careers in microelectronics has steadily declined, even in areas like chip design, which have not been outsourced. So my question is, can we turn this trend around? And if so, how?
Thanks for the question. It's a challenge, and I think it would be sort of not appreciating the challenge to just answer, yes, we can turn it around, because it's going to take a lot of effort and intentionality from multiple folks in different areas. It's not something that just one of the schools within the college can tackle on their own, but one of the big issues is that once students are even aware of some of the specialized areas within microelectronics, they've already made career decisions. They've already started having co-ops, internships, thinking about who they want to work with. Long after they've made these decisions, then maybe they are eligible to take an elective in, radiation hardening or something. So what's really critical is that is raising awareness and exposure at an early point so that students can begin building that awareness before they necessarily go deep into the content. So one approach that is particularly promising that we've been seeing is with Professor Moore using context of microelectronic areas within first-year engineering curriculum. And so we've seen that by just giving students very little context of the microelectronics areas still map to the same data science learning objectives that they had in the course, that by the end of the semester, students have increased significantly in their exposure and understanding, just generally speaking. So when you think about, radiation hardening, that's not a phrase that the general population has any even awareness of. And so for students to be picking these things, we need to very early be giving them opportunities to hear about what these areas are.
Okay.
Okay. Well, first of all, thanks, Mark, for having us. So there are a few other things that I can add to Carrie's excellent remarks. So first of all, it's very important that students understand the motivation and the rationale for going into these specific areas, why it's important to meet the needs of humanity, essentially. Because a lot of students will hear a lot of good things about certain topic areas that are considered to be hot topics. And they know that those are important, like they're societally important and they're important for solving critical challenges in society. But they don't necessarily know, why would radiation hardening be important? Like why does that matter? So it's both exposure, but also awareness of the importance of these specific topic areas. And I would say in general, there has been a lot of exposure for students to new types of software. So a lot of students are interested in software engineering, which obviously is important, but they're not necessarily aware of what kind of hardware is driving the designs. And I would say the Scale program is really aiming more at the hardware side, but we are recognizing that some students need to be trained in the software aspects as well, but we're trying to go for a balanced approach where students are aware of both the hardware and the software, why those are both important for the national interest and how they can address that. So I think it's early exposure, awareness of the humanitarian impact, and also raising the awareness that all kinds of students can enter this field. So being very inclusive in our messaging is also important. So every student feels like they're welcome to join these areas. And so that requires a different type of messaging than we've used in the past.
Yeah, thank you. So Anand, you were telling me earlier about some interesting things that high school and undergraduates are doing. Could you share that with the audience?
Absolutely. Thanks, Mark. Yeah, first of all, I think this is a great step forward, celebrating and highlighting the importance of this area. But I think what's more important than highlighting the successes of our students. So I'd like to take the opportunity and share a few stories which I think they inspired me. The first is Sam Zalouf, who as a 17-year-old in his parents' garage in New Jersey, built a working fab in his garage. And today, he's taped out, he's created, manufactured chips with 1,200 transistors and 300 nanometers, right? I mean, that's not 3 nanometers, but that's mind-boggling if you think of him just doing it in his parents' garage. The second is, one of our very own, Joseph Bushagor, who I just was recently reading about this new open source hardware framework for TinyML. And for those of you who don't know what that means, it's getting machine learning into really tiny devices. And I saw that Purdue was involved. I thought it was going to be one of my colleagues. It's a sophomore, actually a junior, now a junior, and he contributed, played a critical role in this open source project. And then I'd also like to call out Zachary Ellis, who is currently one of our seniors here in ECE, who learned about Google and eFabless's free program to tape out chips, and using entirely open source tools, on his own, taped out a chip that was fabricated by Skywater. So I think we have existential proof that we can, and I think the messaging to all of our the next generation of talent should be this is cool, this is important, and you can do it. And I think we need more Sams and Josephs and Zacharys if possible.
Okay, all right, thank you. Well, sort of a related question. Let's see if you have any additional thoughts on this. Another challenge for the workforce, especially for the defense microelectronics workforce, is that relatively small numbers of domestic students are choosing careers in microelectronics. This is one of the primary missions of Scale, to build up the defense microelectronics workforce. Do you have some ideas about why this is the case and what we can do to address this particular workforce challenge?
Can you tell I'm like, let me answer. Yes, we have a lot. First, it should be of no real shock to anyone that there's a decrease in young people in the States going and working in defense. When we think about the messaging that the Department of Defense has done historically, they've really targeted a particular type of person. And the younger demographics are changing very much. And young people haven't necessarily seen themselves as fitting in, or does the DOD want someone like me? There have been 2 reports, one was in 2017 and the other was in 2021, that actually looked at millennials in the DOD STEM workforce and their turnover rate. And when they were talking to the young folks about, why they had left, issues of like the DOD being seen as more traditional and not innovative, or that they felt like it was more rigid, that the workplace culture still seemed very traditional, and what they are looking at is other organizations that would be hiring. So if we think about who would be the competitors of the DOD once the students are graduating, we're talking about Apple, Intel, Tesla. And when all you have to do is pop on those websites and see how they are messaging millennials, Gen Z, very specifically. I had some examples written down here, like Apple says, join us, be you, you're more powerful than you think, and you belong here. I mean, those kind of messages. When I talk to my nephew, who is a sophomore in high school, Southern Indiana, wants to be a Purdue engineer, comes from a Purdue engineering family. And I said to him, I wanted to talk to him about the Scale program. And the first thing he said was, I don't want to work for Department of Defense. I'm like, well, why not? I don't want to fight. So I think there's no awareness at the general population level of the number of engineers that DOD hires, and the importance that they play to our everyday security.
Yes. And by the way, most of the microelectronics engineers are not expected to get into combat. But in addition, I'd like to point out that there are a lot of things we can do to support students in making their career choices as well. And so a lot of what Carrie Douglas has taught me is that there is basically a theory that predicts the choices that students will make in terms of their careers, called social cognitive career theory. or SCCT. And what that tells us is that while personality plays a role, support plays a huge factor. So all the types of support that we can give to students in making decisions about their career, both in terms of providing awareness, providing motivation, but also in terms of providing resources to those students to learn about these topics and to get engaged is really critical. And so for Scale, what that means is more than just traditional classes. So it means like innovative types of classes, as Carrie touched on, as well as both like the intro type classes being basically reformed to reflect kind of the current needs of society, but then also like these upper level specialty courses being created for the first time. But then you also need to have projects, so students get involved in specific projects that are really exciting and interesting, so they actually learn about how they can use microelectronics in a real context and solve a real user problem. So that teaches students about like why these are such important topics. But then there's also research opportunities where they go beyond doing like a short project to something where they can actually like write papers and get like a national and international audience for their work. And then finally, like working at the companies and the government organizations through internships where they actually get real world exposure to the types of problems that these organizations are trying to solve. And then that can provide a pathway to potential employment after graduation as well. So all those different aspects of support are really important. So in other words, we need to invest as many resources as we can into fully supporting students' exploration and career decision making in order for them to feel like motivated and excited about going into microelectronics.
All right, thank you, Peter. So maybe I'll put Jorgen Anand on the spot too. That the challenge with domestic students is a special challenge at the PhD level. Do you have any ideas about how we can attract more domestic PhD students in microelectronics?
So Mark, of course, that's an extremely difficult question. But what I realized is I've tried some new things over the last couple of years. And one of those things was to be more embracing young junior, senior students before their bachelor and invite them to my teams and group meetings. And it sounds like something that, well, I should have done earlier, but you know, in my field, experimental work, it is very difficult without long training to actually become productive, so I thought. But these young students, domestic students that got to know the team and started to work in the team, and sometimes just looking over the shoulder of some PhD students, suddenly realized, wow, that is really interesting stuff I didn't know. And it's kind of echoing with what Peter said about internships, hands-on exposure, but I want to emphasize teamwork. I think feeling left alone as a student is the worst part, right? Trying to think it through by yourself is an impossible task. And so from my perspective, this has had a big impact, and I managed in this way to create a tiny bit of a pipeline, and I can only do so and so much, but it sounds like an idea that might work.
Mm-hmm. Good.
Yeah, the situation is indeed, pretty challenging. First, I think we should acknowledge that. And I think we should also acknowledge that the solution is typically way more upstream than we try to address it, right? So for that, what I mean by that is for increasing the undergraduate student population, we need to go through K-12, right? And I think traditionally what has been challenging is many of the topics in microelectronics have been kind of very specialized and not very accessible. But I think that's changing thanks to the open source hardware movement, for example, right? You can install all the collateral you need to design a chip on your laptop just the way you install a software package, right? And so I think we need to, at the K through 12 level, give this exposure, right? I mean, there's robotics is a great example of all the robotics clubs, and I think it has had a very tangible effect on students coming into either wanting to do coding or maybe mechanical engineering. I think we can do the same with microelectronics. Similarly, I would concur with what Jorg said is, at the graduate level, we need to go upstream and maybe catch them as sophomores and juniors and invest the time to give them the right exposure.
Okay, all right, thank you. Listen, I don't know who's keeping time here, but I will ask one more question, and then if we have time, we might have a few questions from the audience. So my final question, what characterizes U.S. universities is a tight connection between research and education. We generate new knowledge and we disseminate knowledge. In 1959, electrical engineers were still being taught vacuum tube circuit design, but transistors were taking off. And beginning in 1960, we reinvented the electrical engineering circuits curriculum to focus on solid-state electronics. And we designed a curriculum that was well-suited for the Moore's Law era. We're at an inflection point now. We heard from Jorg and Anand at the beginning of this discussion. Things are changing. We have to find new ways to advance electronics. Microelectronics is changing. How does the microelectronics curriculum need to change?
Okay, I'll take that one.
Okay.
So I think, first of all, there are a lot of things that we're doing right. So I think we should recognize that. Like, we are getting students engaged in kind of the fundamentals of electronics at a very early stage. They're learning some about it in first-year engineering. When they get to sophomore level, they oftentimes will also take in-depth courses. And we've actually reformed the curriculum at Purdue already to focus on what we call Fundamentals 1 and 2, which is kind of an innovation from what we had before, which was linear circuits. And so when we did linear circuits, that was giving people a partial picture of what's going on. But in order to make the math simpler, we were leaving out these very important devices of transistors and handling it in a separate course. But now it's kind of integrated into the curriculum from very early stage. So I think that's a good thing. We need to make sure students understand both linear circuit elements and nonlinear circuit elements. But then furthermore, they need to understand more of the software tools at a very early stage. And so another thing we've been doing is introducing tools where students can simulate what's happening in circuits very early on, including sophomore level. And there are resources that are run out of Purdue, such as NanoHub, that provide resources for students to get involved in running simulations and having kind of hands-on exposure and connection. Also being able to run software tools like SPICE that give you predictions of circuit performance. But then another thing that's important, as Anand was talking about, is being able to do projects on circuits at a very early stage. So again, more project-based courses and opportunities is very important, not just for students' interest and engagement, but also for their potential employers. Because when we talk to employers, the number one thing they're excited about is projects and research experience, typically in a team context. They're not as excited about students just going to lectures all day and just kind of sitting there passively. So actively engaging the students is very critical. First-year engineering is doing a lot in that front, and I think that that's something that's becoming more of the modus operandi in the sophomore through junior and senior level classes as well. And we should encourage that transition to more projects, more engagement, and more interaction in teams for the students. Students love to do team-based projects nowadays. And that is something the more we can basically build it into the curriculum, more active and engaged we force the students to be, the more they'll thank us for it later. Typically, the students who write us letters after they've taken the classes are those who have basically gone through the curriculum and had a teacher who really interacted with them and had a lot of demonstrations, projects, other things that just go beyond the standard lecture. So we have so many more tools. We have hybrid learning techniques. We have lots of videos, tools, simulation tools, et cetera, that we can basically bring to bear on these problems. And then of course, connecting students with the real world context is something that we can do in the classroom from the very early stage, and that's something we're trying to implement and scale. So, well, that just kind of scratches the surface. There are many things we can do.
Mm-hmm. Okay. So we hear more and more about the need for full stack engineers. I wonder if Jorg or Anand could tell us what a full stack engineer is and how we educate full stack engineers.
Yeah, I think a full stack engineer usually refers to somebody who has sufficient understanding of different levels, of abstraction, right? I mean, as we know, designing chips, the term originated, I would say, in the software context, but I think it is being applied increasingly to the hardware context as well. So I think we need to be making sure that there is a certain minimum level of breadth that our students have across devices, circuits, maybe architecture and systems. And that is, I think, starting to happen with some of the curriculum reform or innovation that Peter talked about. We have some of our new credentials, both at the graduate and levels and undergraduate levels, including a specialization in semiconductors, a master's program. You can learn more about that on the Purdue online. But I think there we are starting to see some of these changes already happening. But I think we should encourage students to, not just be siloed. Increasingly, going back to what I said about where the improvements in the next decade are going to come from, co-design is going to be essential, and that, that leads to that requirement of people who can understand and at least work. Even though you might specialize in one area, you need that breadth, in other areas as well. The other thing I just wanted to mention is, going back to your earlier question, if I might, is, in addition to whatever Peter mentioned, I think any student who is interested in designing a chip should have an opportunity to do so. Mm-hmm. And I'm really proud to say that at Purdue ECE, we are kind of already moving in that direction. We still have some ways to go, and shout out to Mark Johnson, who runs the socket team, that is providing such opportunities. Of course, Mark, if we could clone you, we'd be happy to do that. But we need more. We need more of that.
Yeah. All right.
Thank you. So we heard a little bit about how important internships are, and internships are at various places, industrial places, obviously open the eyes for these students to see a different perspective other than what they learned in class. But I wanted to bring up something that I think is equally important. So if we want to really build this well-educated student, to squeeze more into the normal curriculum is not possible. We know that. At the same time, there's more and more knowledge. So what can you do, right? I have two boys that went through Purdue and finished their studies, and we were thinking about how to become more effective in learning. And I think this summer is a wonderful time actually to join some of the research activities. And yes, the students will probably not like to hear that, but if you want to be serious about a complete education, think about a smart way of using the summer interns from the very beginning. Spend some time doing research, go into some of the industrial labs, and get a picture that puts you well beyond what you normally learn just through the classes.
Thank you. So, how are we doing for time? Who's keeping time? Do we have time for a few questions from the audience? We do. Okay. Is there a question from the audience? Jay, you always have a question.
I think you mentioned involvement of undergraduates in the research, and certainly at Purdue we pioneered that, and so many students do get involved in undergraduate research. Back then and over the years, we have also thought of something we called high surf, as in high school students in summertime working in Purdue research laboratories. And I think Georg mentioned that idea. Would either one of the centers aspire to involve high school students early in university research so they can start thinking about future careers early in their high school junior and senior years?
Mm-hmm.
Yeah, I can speak to that. So first of all, I think it's very exciting when high school students want to do research. I mean, that's fantastic, right? Now, it is a fairly labor-intensive effort. So I'd say if the resources are available to support high school research, then that's fantastic. And I do know there are a few programs that support that. It's going to be probably hard to support that for every high school student, but there may be some selective students that we can pick where we have sufficient volunteers to get involved with that. But another thing that could be very impactful is an approach that was pioneered by Tamara Moore, which is basically leading teacher workshops to develop new types of curriculum. And the advantage there is twofold. Like basically the teachers can learn about these topics in microelectronics that they may or may not have been exposed to when they were in college themselves, and then basically bring that to the curriculum, like these new topics and new contexts that they might not have known much about before. But then second, they can also use new types of teaching beyond the standard lecture approach, like active learning, like different types of modules and projects, including team projects. So I think like getting students involved with like these active hands-on learning activities is absolutely critical, for sure. And then I would see high school research is kind of like the pinnacle of that spectrum of different types of activities for high school students. And if students are really highly motivated and highly effective in their earlier curriculum, like basically they need something that's more challenging than that kind of thing, like at the high school level, then I would say yes, they should go into high school research.
Thank you. Another question?
Sorry, maybe Jorg, you were going to add to that.
If I may just, I think the mentoring here is again important. And who can better mentor a high school student than a young undergraduate? So I would argue that our job has to be to make sure that undergraduates that are themselves trained maybe by seniors or by PhD students, that they understand if they are interested, they can have a huge impact on young high schoolers. We should really use this pipeline.
Is there another
Okay.
question?
Yeah, Mark, I'm going to.
Oh, go ahead.
Yeah, the focus of really thinking very broadly about how we can close the gap on what are staggering numbers. I think I read 30,000 open positions just here in the Midwest with the announcement of the Intel megafab. One thing you haven't addressed, which we recognize is a very significant challenge, is how we engage more equitably across our nation and ensuring that we have representation for women and underrepresented students. And I think that really goes back to some of the comments that you were making about engaging in the high school. So I wonder if how Scale and how CMSE is really trying to address the fact that we need to engage in order to fill the gap with these staggering numbers.
I'll just start, and I'm sure Peter and Kerry will add to that. But first, engaging about high school research. I had a daughter who it was really transformative, the opportunity to engage in high school research, and she's now at Purdue. So I think whenever possible, and students who are motivated enough to do that, we should give them those opportunities. It's probably going to be still a few % of the students, not everybody, but for the others, I do think increasing awareness, having these workshops or maybe camps would be a great way to spark their interest. So maybe a few years down the road, maybe as an undergraduate, then they will get involved. But Teresa, coming to your question, I think it is of immense importance because just the need to fill all of those jobs will force us to think broader than we traditionally have, right? So it's not nice to have, it is a must-have at this point if we are to fill those jobs. I went on LinkedIn yesterday, and just in chip design on LinkedIn, there were 20,000 jobs posted. So yeah, the numbers, if you go across manufacturing, is just staggering. I think part of the answer again lies in going upstream. We try to work at the end of the pipeline, and there's only so much you can do by increasing the suction at the end of the pipeline. You need to go ahead upstream at the K through 12 level and at the early undergraduate level. But I know Purdue, for example, has some very good partnerships with some other institutions, minority serving institutions. I think we need to, as faculty, invest more time in leveraging those partnerships and figure out how to do this in the most efficient manner, right? So we use our time most effectively to achieve an impact.
Yeah, thanks, Teresa, for the question, because I think it's kind of like the elephant in the room. And so just pragmatically speaking, achievement differences between black and white students on standardized tests as early as elementary school, I mean, is a standard deviation. So when you think about, like, we can talk or debate all day about systemic racism or blame the students or blame the schools that have poor funding, but the reality, that's just the reality where we're at. And so if we continue to rely on only the students that meet our like standardized test cutoff scores to get admitted, like Purdue will never increase in diversity because there won't be enough students to draw from the population, which is my understanding has been sort of the long-standing argument. There are other places except like HBCUs accepting students with different cutoff scores for admittance, and those students are going on and being very successful. So that's one, like, if we keep doing things the same, we will not get different results. And the other is, there is a lot of opportunities with thinking about these positions that are not just at the bachelor's degree. And so I think that's part of, like, right now we're leading up a proposal that would essentially be developing a consortium with the community colleges in Indiana, Ivy Tech, to be able to work with them on a certificate program at the associate level. And again, when we talk about and when we hear from our DOD partners, they tell us they need technicians, you know, just as much as they need the engineers. So I think that that's important. And then also the pathways in. But I think, so in terms of like practically like curriculum that is relevant and exciting to a variety of folks, that when we ask questions on exams that we think about, you know, in our attempts of getting real world experience, that this real world experience is reflective of a diverse group and not just my experience. So for example, I have a colleague who the very first time she ever thought deeply about snow was on an engineering exam, and it was having to do with the snow and on the trusses and the pressure and the force. So that would not be the time that you want to be thinking about how dense is the snow, how fast is it going to melt, and what does this mean in my design. So just thinking about, I think we each have our own role to play in making things equitable and taking responsibility for not just assuming that my way of living or what I know is what everyone else does. But then I think for us to actually make a big difference, we're gonna have to really think about how important is this to us and what are we really willing to do about it.
Thank you. Just one more thought here, that I think many of these institutions may not have a critical mass of semiconductor faculty to offer a broad curriculum in microelectronics. This may be an opportunity for us to use our strengths in online and offer students at these institutions an ability to minor in microelectronics, to design a chip, to do some things that they might not otherwise be able to do. So, Tamara?
Tamara, yeah.
Tamara.
Hi, everybody. I actually want to add on to the conversation about the how do we attract others, because there's a piece to this that I think all of us can learn from that is actually incredibly practical. When you are asking questions or putting things in front of students, you want to show them that the thing you're doing is exciting. So we've talked about that a little bit. How do you do that? You actually take a step back, and you start to tell the story about where this thing is going to be used. You know, if you talk about, you know, these chips that are going up into space for like missile defense, you're going to lose a whole bunch of people quickly. But if instead you talk about that it's going off to explore Mars, you're going to increase the types of people who might be interested in it. So how you tell that story, if you can show how this kind of work will save the world. And I'm not kidding about that. Like, you know, it's kind of a tongue-in-cheek thing on one hand. But if you really, even it only takes a couple sentences in your story that you're telling about the problem that you're going to have your students work on. But if you just give them that sense that it's bigger than the math that you're doing to model this chip or whatever, and you just give them that sense of sort of belongingness, the interest increases. And so it's something we can all do in whatever context we're working in, but using that as a way to get students excited about this is really, that's the key of like what we're doing in first year, because we're still teaching them to code and to think about design and all those things, but we're putting cool stories on top of it that are microelectronics related.
Right. Thank you. Okay, maybe one more question right behind you, tomorrow.
So I've mentored a lot of student teams over the last few years, and one thing and we're moving a lot more towards project-based learning, which I think is very exciting. And so one thing that comes along with project-based learning is that there's an increased variability in outcomes. Because there's, you know, if you give somebody an open-ended project, they could go one direction and go another direction. So what can we do to ensure that we are getting consistently positive outcomes from project-based courses? And then along with the equitability discussion, a lot of times if you have teams that have more students with different backgrounds, you can lead to significantly different outcomes. So I guess really, how do we ensure consistency in positive outcomes for all of our students, not just the high-performing students, not the, you know, sure, yeah, a student that built a fab in their garage in high school, probably when they come and work on projects here, they're going to do well on their projects. How do we ensure that the student that didn't have the resources to build a fab in their garage in high school can still be successful on a project team?
Does our panel have some thoughts?
Yeah. So thanks for the question, Sun. That's an excellent question. And of course, it's not a trivial question to answer, but I would say one thing that's really critical is having some sort of intellectual scaffolding. So in other words, there's like a substantial amount of structure built into the course. So while students are working on open-ended projects, they also have a design process and a way of thinking through everything that they're doing like systematically, and that's being guided by the instructor, not constrained, but guided, so that you can kind of progress through the steps in a logical sequence and not leave out anything important, right? So I'd say like the structure is very critical, but then the second thing that's really important is support. So basically that students are fully supported in what they're doing. So having TAs and other resources, other people that have technical expertise. In the case of like ECE 49022 and 477, the ECE shop and the TAs, as well as the faculty, are all important resources for the students. And then there are other types of resources that could also be added that would be helpful, such as having the ability to reach outside experts, like particularly if it's like related to some particular application that those experts are interested in. And then also having the ability to purchase equipment and other types of things that they would need in order to be more flexible in their design choices.
Okay, thank you.
I don't have a silver bullet answer here, but I think it's an important question. Two things I do want to emphasize. I think for the project-based courses, the hands-on support, you need the lab staff and the TAs who can spend time with the students, help them debug. I think, you know, a lot of the variability in outcomes, in my understanding, I teach at the graduate level a very hands-on course, relates to the ability to debug. I think we need to teach that as a skill throughout, but also accept that, you know, students will come in with varying abilities on that dimension, and just have the support staff. And, you know, ECE is, you know, good in terms of investing in TAs and lab staff, and I think we can always do better. The other, of course, is, you know, from a grading perspective, maybe we can rethink how we grade, and there could be a component of the grade that is, certainly you want to have some absolute criteria, but maybe if there could be something related to the growth that a student experienced relative to where they started off, I think that would be more rewarding to a broader range of students as well.
Yeah, thanks. So, all right, brief remarks, okay.
I got the finger from Mark.
I'm looking at Teresa here.
So students come to us with a variety of experiences. I have met students who didn't take a single programming course at their STEM high school and then got placed into our honors program because they had done so well, you know, and they qualified. But then as soon as they got into the first year courses, they completely bombed because it was moving too fast. They'd never had exposure to programming. So the challenge is having a school as large as ours, or a college as large as ours, but still being able to see what the individual needs are and that we are supporting them with where they come in at. And actually, in terms of assessments, there's all sorts of, I did a look real quick, sorry, Mark, last comment. I did a look and at the over 5 years' time at Purdue, the required sophomore courses. And what I saw was that the courses that were primarily based off of exam did have racial discrepancies, but that the courses where there were more project-based and team-based, those discrepancies in scores were not present. And so I do think there is something about the assessments and how we test, and there's something in there.
Okay, all right, thank you. Great discussion. We could go on for another hour, but it's time to close. So before I wrap up, and we asked Teresa Mayer, Executive Vice President for Research and Partnerships, to make a few closing remarks for this celebration. Would you join me in thanking the panel? Okay, Teresa, I think you could.
All right, thank you, Mark, and thanks to everyone on the panel. I will try to be brief because really the conversation in the panel was far more important than closing remarks. But I do just want us to step back and reflect on the fact that this is a really exciting time in the U.S. And if I'm assuming everybody in the audience has been tracking this area for many years, and we kind of went through a phase where there was significant offshoring, particularly of manufacturing. Design has remained strong throughout. The U.S. is still, I think, the largest consumer of offshore manufacturing through design and co-design. But as manufacturing is coming back online, just over the last year, we've had announcements of major investments in new fabrication facilities from TSMC, Samsung, and most recently Intel, right next door in Ohio, in Columbus, Ohio, just about a month ago. And so as we think about our role as a public land-grant institution, and particularly a public land-grant institution in the Midwest, wow, this is going to be the largest fab in the world, and it's within 250 miles of Purdue. So it's changing the dynamic. We have always sat between the very significant growth on the East Coast and the West Coast, but now this is coming to our backyard. And what that's going to do is bring a significant supply chain to this region. And just some exciting facts as we think about talent. If you take a 300-mile radius, we, as a collection of major Tier 1 research universities and smaller universities, graduate probably the highest concentration of degrees awarded every year in engineering and science. And so it's a great place for the semiconductor industry to find a home at last. So it's a really exciting time. And again, the conversation that we had today here on scale and CSME that is really all about the talent, all the way fully integrated from undergraduate all the way up through PhD training and beyond. And the infusion of the internships is really aimed at addressing some of those staggering gaps in the positions that we need to fill. But also, now that manufacturing and design is really coming back, it'll place the U.S. in a position where we can truly lead in the development of next generation technologies. It's hard to do that when you don't really, you're not advancing state of the art in the manufacturing aspects. So it is a really, incredible time. As I returned to Purdue, and this is my own area of research, or at least a small sliver of this, one thing that, I think sometimes we lose track of is the fact, too, that at Purdue, as you look at from end to end, I say from atomistic modeling to materials to devices to design, co-design of energy efficient architectures to packaging to thermal transport and management. We lead centers, major national centers, in every single vertical along that pipeline. And now we're bringing those all together. So as we conclude, not only celebrating Scale and celebrating CSME, which are very significant programs, and I do want to point out that Purdue alone can't really tackle this huge gap. And so importantly, both of those initiatives are national. It's really working with a network of universities, and Purdue's leadership to really drive that forward is very critical. But I'd also like to acknowledge the faculty, leaders, and participants, and students and postdocs, and staff who are part of all of the centers in each one of the verticals. Mark from launching the Nano Hub to Gerhard and Ali, who continue to carry that forward almost 20 years after the launch. We lead one of the major jump centers, Seabrick, that Kaushik and Anand lead. We have two of the NCOREs, New Limits and Capsule, that Jorg and Zihong lead, as well as an SRC packaging center together with SUNY Binghamton that Ganesh leads. So, and I should not fail to mention, again, our IUCRC in thermal management. So I'd just like to conclude again by celebrating all of the successes and the very strong commitment that our faculty have to really ensuring that we continue to advance the state of the art and the technology and really address these critical aspects of our economic prosperity and our national security through our deep work with the Department of Defense. So thank you to everybody.